Hi, I'm Simone Bottoni and I'm a PhD student at the University of Insubria in Italy. Today I will present our work, Privacy Preserving Distributed Support Vector Machines. We are in a scenario where we have some hospitals that want to train a machine learning model. To do that, they must share their patients' private data between them. The problem is that if some of these hospitals are located in different countries, maybe they can't share their data across borders given the country's privacy rules. So to solve these problems, the hospital can use a federated learning model, but it is also subjected to a different problem. In our case, we consider the inference attack. So to allow to hospitals to train a secure federated learning model, we develop a novel secure multi-party computation method that can be applied to any federated learning model. Our protocol is based on the homomorphic encryption scheme. So to illustrate how our protocol works, we apply it over an existing federated learning algorithm called Cluster Parallel Dual Split, or CPDS. And then we test the secure version of CPDS in an healthcare scenario over some health disease dataset. So first, we briefly present how the CPDS works. CPDS assumes that there are P agents that want to train a sparse hypervector machine model. Each of these agents own a set of data, and in an iteration works both as a simple node and as an aggregator. So CPDS works in this way. At each iteration, each agents compute its algorithm coefficients and then send these coefficients to all its neighbors. When a node received all the coefficients from all its neighbors, it can sum all these values, obtaining an aggregated value. The node can use this value as input for the next iteration. Our method is based on the homomorphic encryption scheme. So the first step of our protocol is the keys generation. So to do that, we suppose a trusted entity that generates the keys and distributes them to the nodes that want to participate to the computation. The entity generates for each node a master private key that the node uses to decrypt the aggregated value, and a set of M secret encryption keys, where M is the number of nodes neighbors plus one, that is the node itself. The entity distributes M minus one of these of the keys of the set to the node's neighbors that use a neighbor use this key to encrypt its coefficients and then send the encrypted values to the corresponding node. The peculiarity of the keys that are present in this set is that they contain a random value that is different for each key. And we also impose that the sum of all these keys, of all these random values, are equals to 0. So the encryption of message M with one of these keys is the encryption of a message M plus the encryption of of a random value. When all the nodes receive all the keys, the nodes can start the protocol. In our protocol, first we assume that each node has at least two neighbors, and our protocol works in this way. At each iteration, each node computes its algorithm coefficients and then encrypts these coefficients with m times with the m keys that corresponds to the node's neighbors, and then send these encrypted value to each of these encrypted values to the corresponding nodes. When a node receives all these encrypted values from all its neighbors, it can sum all these values. In this way, all the random values that are contained in the encrypted coefficients must go to 0. In this way, the node can decrypt the encrypted aggregated value with the master private key. And then it obtains a plain text, the aggregated coefficients that the node can use as input for the next iteration. Using this random value, a node can't obtain the exactly coefficients from one of its neighbors if before the node sums all the other's values. In our protocol, we assume that each node has at least 2 neighbors. But if we consider also the other case where we have a node with only 1 neighbor, as in this case, we have a problem. For example, in this case, if we consider C, that is a node with only B as neighbor, when C receives the encrypted value from B, C can sum its value with the B value and can decrypt the aggregated value. Given the fact that C knows its value, it can easily obtain the B value. To solve this problem, we develop a variation of the protocol that use dummy link. So the key generator entity that knows the topology of the network, when see a node with only 1 neighbor, generates a third key that distributes to a random node of the neighbor of the node with only 1 neighbor. For example, in this case, for example, the key generator entity distributes the key to the node A, and C received the encrypted value from B and also from A. In this case, we consider the protocol as our normal protocol. We also prove the fact that our protocol is the security of our protocol. To do that, we suppose that a scenario, a non-est but curious scenario, and we also suppose that our protocol is insecure. We consider an adversary that can intercept and decrypt all the messages that are present, that circulate in the network. Then we consider, to prove the security of our protocol, we consider an encryption of message M with one of our keys. If we impose that the random value is equals to 0, we can obtain an encryption of a message M with the standard Paylier protocol. Given the fact that we know that Paylier protocol is secure, so we can consider our protocol secure. Then we test our method, and to test our method, we consider different environments. So first, we consider the number of nodes that want to participate to the computation, and then we also consider the topology of the network that connect these nodes. We consider 3 different topology: a low connected network where we have a low connected node, and in this topology we can apply the protocol variation. And then we also consider a partially and a fully connected network. We also use 3 different datasets to test our method. The first one is a synthetic dataset that we generate in 3 different versions. These versions have 5, 10, and 20 features respectively. And all of these 3 versions has 15,000 of instances. Then we use the 2 datasets that regards the air disease problem. The first one is the air disease dataset that describes the air disease problem in the Cleveland population. And this dataset has 303 instances and 14 features. Then, given the low number of instances of this dataset, we choose to use another dataset that is the Framingham one that described the cardiovascular disease problem in the Framingham population. This dataset has more than 4,000 of instances and 15 features. To evaluate our protocol, we consider the time that the total time that we added to the CPDS, to the computation. So we consider the secure version of CPDS, and we recorded the time that we added compared to the non-secure version of CPDS. We can split this total time in 3 different subtimes. The first one is the encryption time. That is the time that a node used to encrypt all the values in an iteration. Then we consider the sum time. That is the time that a node uses to sum all the values that is received from all its neighbors. And finally, we consider the decryption time. That is the time that a node uses to decrypt the aggregated value. Then in the following slides, we present some results that we obtained. The first result that we present is the total time that we obtained with the synthetic datasets. The total time, as I previously said, is the sum of the 3 metrics. So in this chart, we present how the time or how the total time that we added increased with the number of features, and also with the number of features of agents, and also with the number of edges. That is the network topology that the 3 different network topologies that we consider. And we also obtain the same results with the same dependency also for the other 2 datasets. In this chart, we show that the 3 components of the total time. So we can notice that a node use more than 96% of the total time only for encryption. Then we also test the precision of the secure version of the model if our secure version of CPDS has the same precision of the non-secure version of CPDS. So we use as metric the AUC. And from this chart, we can notice how the encrypted version and the not encrypted version has exactly the same AUC. We also test if the variation of our protocol impacted on our on the AUC, on the precision of the model. In particular, considering the AUC as metric. And from this chart, we can conclude that the variation of our protocol didn't reduce the AUC of the model. In this chart, the results are not perfectly the same because CPDS requires some initial parameters that are randomly generated. Finally, we can conclude that the time that we added to the secure version of CPDS depends on the number of features, the number of nodes, and also on the topology of the network, but it doesn't depend on the number of instances of the dataset. We also prove that our protocol is secure, and also that it preserves the precision of the model. Finally, as future work, we are interested into improving the time that we added to the federated learning model. For example, trying to reduce the number of encryption that a node must do. Another future work that we consider, that is interesting to consider, is to consider different attacks from the inference attack. Thank you for your attention.